Hello, Chem 1110 students. We're going to finish off Chapter 4 by looking at some more properties and periodic trends in the periodic table. So we've looked at metallic character before, and I've shown you this periodic table where all the metals are a light green. And these are the characteristics of metals, one of the most important being they conduct heat and electricity well. The other thing is they have low ionization energies. They don't hold their electrons tightly, and therefore they readily form cations. Non-metals, we've looked at these, they're blue on this periodic table. One of the big things is that they don't conduct heat and electricity well, and they have high electron affinities, meaning they tend to take on electrons. They don't give them back, so they don't conduct electricity, and they commonly form anions. Metalloids, of course, are in the orange here, and their characteristics are somewhere between the metals and the nonmetals. All right, so we're going to start talking about ions and the electron configuration of ions because it will help us understand their chemistry. And we're going to look at how you write the electron configuration for an element of a main group element. Write the electron configuration for an ion of a main group element. So first you write the configuration for the atom, and then you add or move the electrons that you need to or want to. So for sodium, the last electron is at 3s. It's the furthest away from the nucleus, comes off readily, and you can see that it now has a filled s, quantum number 1 shell, and a filled quantum number 2 shell. So it's isoelectronic with neon, which makes it extremely stable. The next one is chlorine. And chlorine has 7 valence electrons in the s, or in the 3 principal quantum number. It readily takes on 1 electron, which fills its 3rd quantum number electron shell. And so it becomes isoelectronic with argon, once again making it very stable. It's a new term. Isoelectronic means the electrical or the electron configuration for the ion is exactly that of a noble gas. So we're going to look at some common monoatomic ions according to their position on the periodic table. And you can see that the first 2 groups, the alkali metals, the alkaline earth metals, make +1 and +2 cations, whereas your anions happen to be in that top right-hand corner of the periodic table. And then we see some examples of the ions you get from transition metals. Excuse my dog barking. So we're going to write some electron configurations for some main group elements here: nitrogen, barium, and beryllium. We're going to first write the electron configuration and then add electrons to nitrogen and remove electrons for barium and beryllium. And here's the answer. So sorry, I had to move my dog out of the front window. All right, so nitrogen is in the 2nd row of the periodic table. So it's a 2s2, 2p3, and it would like to be like a noble gas. So it happily takes on 3 electrons, which makes it a 2p6, makes it isoelectronic with neon. The next one is barium. Barium is in the 6th row of the periodic table. And so, did I count that wrong? 1, 2, 3, 4, 5, 6. And so it would be a 6s2, and leading up to that, of course, it has the 5s2, 4d10, 5p6 filled. So it readily gives up those 2 electrons that they're in the 6s2, and that gives us this electronic configuration, which is isoelectronic with xenon. And then the last one was beryllium. We're back up to the second row of the periodic table. It's a 1s2, 2s2. It's happy to give up those last 2 electrons that were added. They're much further away from the nucleus, and so you end up with an 1s2, which is isoelectronic with helium. All right, so what about D block elements? So these are what we call the transition elements. Why do they form more than one ion? Well, the way most ions are formed for the transition metals is you take off the electrons from the highest value of N, so they are the largest S orbitals, and then you can start taking off P electrons. So if we look at iron, iron is in the 4th row of the periodic table. So we have a 4s2 and then a 3d6. So in order to form an ion, we take off those 2 4s electrons, and we are left with a argon shell with a 3d6. If we want to form the iron 3+, then we have to take one more electron off, and that has to come out of that 3d subshell. But what you end up with is the core of argon and then a 3d5, which is a half-filled D energy level. It's half-filled. The electrons are not sharing any of the orbitals, so the repulsion is down. So it's a very stable electron configuration. So we have some examples that we want to write. So zinc and manganese. And once again, you start out writing the electron configuration and realize that when you make these ions, you take the S electrons first. And so if you look at zinc, zinc is in the 4th row of the periodic table. It is the last of the D's to fill. So it's 4s2, 3d10. You take off those 2 4s electrons and you're left with a 3d10. For manganese, manganese is 4s2, 3d5, and so you just once again take those S electrons off. All right, so we're going to talk about ionic radius, and so once again we're looking at size because this can be important in forming bonds and chemical reactions. But this is the ionic radius of an ion when you have taken away electrons or added them. So if you remove electrons, you get a cation, and it generally gets much smaller because you reduce the electron repulsion. And so here's just a little diagram of what that looks like. But the bigger thing is that the valence electrons have been removed and there is more positive charge in the nucleus, so it really pulls those electrons in. And so we have a diagram of this in the this little picture on the right hand side. And so the way you read this, if you look at lithium, it's got 152/76. And so the size was originally 152 and it's dropped down to 76. So it is half of what it was. And you can see that when you go to the non-metal side of this, that they go from being smaller to being larger because you've got more electrons than you have positive charge in the nucleus, and so they spread out even further. So cations get smaller, anions get bigger. So if we want to compare these ionic radii to the atomic radius, it's just what we said. We get more electron repulsion and anions, and so they get bigger, which is what I just spoke about in the last slide. And that's it.